All right, today we want to start chapter 3. Chapter 3 is all about systems of equations. Now, so far we have looked at single equations, just one line. Next, we're going to be looking at systems of linear equations. So systems of linear equations, a system being a set of two or more equations in two or more variables, and linear meaning we're going to be studying lines. We can solve these things by finding the solution or the set of solutions that will satisfy each equation simultaneously. All right, our first example for chapter 3. It says here the perimeter of a standard tennis court used for doubles is 228 feet. The width is 42 feet less than the length. We want to write a system of linear equation that models this situation. So whenever we are modeling, we're handed a word problem, we want to go through here and start picking out the pertinent information. So pertinent information here, we have the perimeter of a tennis court. And we've been given this number, 228 feet. So a tennis court is a rectangle. Rectangle has dimensions of length and width, and these must be equal. We're interested in the perimeter. Now you might remember the equation for the perimeter of a rectangle. If not, we have to remember that perimeter means the length on the outside. So if I were walking along the edge, I'll just pick up all of these measurements. So I'll say that my perimeter, well, I have a length, and then I have a width, continuing on, another length, and then another width. So if we didn't remember that the formula of a perimeter is 2 times the length plus 2 times the width, as long as we remember what perimeter means, we can always derive that formula. What were we given? We were given that this value is 228 feet. So we know 228 is equal to 2 times the length plus 2 times the width. We got to ask ourselves, can we actually solve this and figure out what both length and width are? Well, no, in fact, this is not enough information to find out what both length and width are. In fact, if I have two variables, and in this case I do, since I don't know what either one of those are, I'm going to need two equations. That's a good general rule. If I have one equation, I can solve for one variable. If I want to solve for two variables, I need two equations. For three variables, three equations, and so on. Good news, we were given more information. What information? We were given the width is 42 feet less than the length. So that tells me my width is 42 feet less than the length. So I take my length and I subtract 42. This gives me my system. I now have two equations modeling this situation. I have the perimeter equation, 228 is 2L plus 2W, and then I have here that the width is the length minus 42. So actually, I could solve for both the length and the width now. All right, so if we're given a system of two equations and two unknowns, the solution to that thing is going to be a pair of numbers, one for each variable, that makes both equations true. You will frequently see this given as an ordered pair. So example 2 says, hey, here's our system. Let's have the system. First equation is x plus y is equal to 7. And the second equation, 2x minus 8 equals y. Let's see if we can figure out, is the ordered pair 5, 2 a solution? So 5 means my x variable. Value for my x variable is 5. And then the value for y is 2. Let's do it on the side here. I'll start with my first equation. It says x plus y is equal to 7. What was x? 5, and y 2. And yeah, I get that 7 is equal to 7, so it checks in the first equation. That's equation 1. Equation 1 we're happy with. Next we check equation 2. That's 2x minus 8 equals y. I put 5 in for x. I hope that that is a 2. Well, let's see that. 10 minus 8. And yes, 10 minus 8 is 2. It checks in both equations. So yes, this is a solution. Okay, here's our second example. Example 3, I guess. Given the following system, first equation is x plus 3y equals negative 7. Second equation, 3x minus 2y equals 12. We want to decide if the ordered pair negative 1, negative 2 is a solution. Let's find out. First equation says x plus 3y equals negative 7. X was negative 1. Y is given as negative 2. Just negative 1, and then 3 times negative 2 gives me a negative 6. Negative 1 minus 6, sure thing, that is negative 7. So it checks in the first equation, bright green check mark. We now check in the second equation. Second equation says 3x minus 2y should be equal to 12. So I'll put in the negative 1 here for x, negative 2 for y. That is a negative 3. Negative negative becomes positive, and that's a plus 4. Negative 3 plus 4 is 1. And 1 does not equal 12. So in fact, this is a lie, and it does not check. So since it does not work in both equations, it is not a solution. All right, in section 3.2, we're going to study algebraic methods for solving systems of linear equations, but right now, let's look at how to do this graphically. So if you recall previously, we said, oh, I can graph two sides of an equation, look at where they intersect, and that gives me the solution. I can do the same thing with a system of linear equations. I can graph both lines and inspect their intersection, and that would give me the solution to the system. In order to do that, these things, I should probably put them in slope-intercept form because I am going to use technology to graph this rather than graphing it by hand. I'm going to just use Desmos, super helpful. So I will put these in slope-intercept form so that I can put them in Desmos and use Desmos to do the graphing for me. First equation is x plus 3y equals negative 7. I'll just begin by subtracting x from both sides, giving me that 3y is negative x minus 7. Then I will divide each term by 3. So that y is, and I'll write that as negative 1/3 times x minus 7/3. That gives me equation 1. Equation 2, a bit too dark, so we'll just stick with the yellow. It's 3x minus 2y equals 12. I will subtract 3x from both sides. So negative 2y is equal to a negative 3x plus 12. Finally, divide by negative 2 everywhere. So that y, let's see, negative negative gives me positive. So 3/2 times x. And 12 divided by a negative 2 is a negative 6. So these are the lines that I will put into my graphing utility. So I've brought up Desmos. Come over here. My input panel, I'll call the first line f of x. We said that was a -1/3. I'll arrow over to get out of the denominator, and that's times x, -1/3x minus 7/3. There is our first line. I'll call the second one g of x. That was 3/2 x minus 6. And there's our second line. Again, mouse to drag things around and have a look here and click the intersection. It tells me that it intersects at the point 2, -3. Okay, I put that graph here in our notes so that we can refer back to it. It says that the solution here, it looks like a point of intersection. This was our point of intersection. And we found that, according to Desmos, that was the point 2, -3. We can confirm this by putting 2, -3 in both equations and checking to see that it makes both of them true. So our first equation, if you recall, was x plus 3y equals -7. I'll put in 2. I'll put in -3. That becomes 2 minus 9, -7, and yes, that is -7. So it checks in the first equation. Let's check in the second equation. 3x minus 2y, and we hope that that comes out to be 12. So 3 times 2 minus 2 times -3. This is a 6. Negative becomes a positive, and 2 times 3, also 6. And yes, 6 plus 6 is 12. So this checks. This is the solution to the system.